So good morning everyone. So this is my next lecture in continuation with the lecture number 14 based on PN junction diode. Earlier what we have seen about the normal diodes, then we have seen about the Zener diodes, and then we will look after about what are the characteristics of PN junction diodes, what are the different types of PN junction diodes, and with these different configurations of PN junction diode, how can we use these configuration in different applications in our semiconductor devices. So in this lecture we are going to see about the PN junction diodes, what are the different types, their characteristics and their applications also. So in the first part, what we are going to see, what is the PN junction diode. So the basic of electronic system nowadays is a semiconductor device. So we have already seen about different types of semiconductor devices like materials, that is indium gallium arsenide or aluminum gallium arsenide or gallium arsenide type of material, and different type of semiconductor devices like LEDs and lasers. So the famous and commonly used of this device is BJT, which is also called as bipolar junction transistors. So these bipolar junction transistor can be used as an amplifier or logic switches, and BJT consists of basically 3 terminals. You can see it consists of 3 terminals, that is collector, base and emitter. So there are 2 types of BJT. First one is the PNP type of BJT and the second one is the NPN type of BJT. So apart from that, if we see about what are the different characteristics of BJT, we can see where it can be used as an amplifier or as a logic switcher. So these are some applications of BJT, and the terminals we can see, that is collector, base and emitter, and the 2 types of BJTs which are PNP or NPN. So it is basically combination of 2 PN junction diodes, which we have already discussed about in the previous classes. So next, transistor construction. So if we see about the construction of the transistor, 3-layer semiconductor devices consisting 2 N layer and 1 P type layer and of material, then it will form a NPN type of transistor. We can see that is 2 N layer and 1 P type of layer, and it will create your NPN transistor. Similarly, if we see 2 P and 1 N type of layer, then it will create a PNP type of transistor. So the term bipolar reflects the fact that holes and electrons participate in the injection process into the oppositively polarized material. So a single PN junction has 2 different types of biasing. It can be of forward biasing or reverse biasing. So thus a 2 PN junction device has 4 types of bias, that is PNP. For PNP we have forward bias and reverse bias. Similarly for NPN we have forward bias and reverse bias. So we will see from the construction point of view how these PNP and NPN will work in a forward biased and reverse biased conditions. So what we have seen, that the BJT or the PNP or NPN type of transistor can be formed with the help of the 2N or 1P type of layer, or similarly PNP type of transistor can be formed with 2P and 1N type of layer, and it has 2 different types of biasing, which is forward biasing and reverse biasing, and it has, or you can say that it has 4 type of different biasings for the NPN types, 2 biasing stages for the NPN and 2 biasing stages for the PNP type of transistors. So if we see about the position of the terminals and symbols of BJT, we can see that we have emitter, base, collector, and it is shown here, that is PNP of transistors. So emitter, base, collector, we have emitter in the P connected to the P side and the collector to the P side and the base to the N side. Similarly for NPN type of transistor, we have emitter, base and collector, and we can see that collector is connected to the N side and emitter is connected to the N side and base is connected to the P side. So if we see the current direction in the PNP and NPN, obviously the current will flow from P to N side. So this is P, this is N, this is P, and the current will flow from P to N side here. Similarly for NPN transistor, the current will flow from, this is N, this is P, this is N, from P to N type of. So these are some pictures which shows the position of the terminals of the PNP and NPN using emitter, base, collector type of configuration, and the current direction basically, because we have to know from where to where the current is flowing. From emitter to base the current is flowing in the PNP type of transistor, and from base to emitter the current is flowing in the NPN type of transistor. So here base is located at the middle and more thin from the level of the collector and emitter, The emitter and collector terminals are made of the same type of semiconductor material, while the base of the other type of material is something different. So, we have to see whether the PNP or NPN type of transistor have different type of current direction from emitter to base or from base to emitter side. So, now we are looking into the transistors currents. So, we have three different currents here. The first one is the collector current, the second one is the base current, and the third one is the emitter current. So, from the picture which is shown on the left side, we have emitter, base and collector type of configuration, and for this we have PNP type of configuration. We have taken PNP transistor here. So, the current is obviously flow from P to N side. So, the current direction is here from P to N side, that is from emitter to base side. So, we have emitter current which is shown by IE here, then there is another current, that is base current, which is IB, and the next current is IC, which is the collector current. So, the electrons will move towards from base to emitter, and the current will flow from emitter to base side, and then the electrons will be collected in the P type of terminal, that is the collector current, that will contribute into the collector current. So, we have IC there. Similarly, for NPN type of transistor, we have this N, this is P, this is N. The current is from P to N side, and the current direction from, because it is from P to N side, so the current will flow from emitter to in a particular loop. Similarly, the current will flow from IC from collector to in a loop, and there is one more current, that is base current. So, the arrow is always drawn on the emitter. First point we have to remember, the arrow always point towards the N type. So, the current will flow from P to N side. So, the arrow is towards the N type. Similarly, the arrow indicates the direction of the emitter current. In the PNP type of transistor, we have emitter to base type of current will flow from emitter to base, and for NPN it is from base to emitter. So, these are some points we have to note it down for when you are observing the picture on the basis of the NPN or the PNP transistor type of transistor currents. So, by imaging the analogy of the diode, transistor can be constructed like two diodes that connected together. So, we can have a two diode combination which can be connected together to form a PN junction diode. So, we have here one type of diode, this, and the other type of diode, this second type of diode, and with these two types of diode connected together, we can form our PNP or NPN type of transistor. So, first one will give you, because this is P, this is N. Similarly, this is N, this is P. So, it will give you PNP type of transistor. Similarly, the second will be, this is N, this is P, this is P, this is N. So, this will give you NPN transistor. So, it can be concluded that the work of the transistor is based on work of the diode. So, we can have the conclusion like the characteristic of the PN junction transistor is similar, somewhat similar to the PN junction PN diode, normal PN diode. So, the BJT has the same type of characteristic like a PN diode. So, both these figures will show you how you can form PNP type of transistor or how you can form a NPN type of transistor. So, in PNP type of transistor, the current will flow from P to N side and it is from emitter to base, and this is your current. And for NPN type of transistor, so it is from base to emitter. So, these are current flowing from emitter to base and from base to emitter. So, now we are coming into the transistor operation. So, the basic operation will be described using the PNP transistor. The operation of the PNP transistor is exactly the same if the roles played by the electron and hole are interchanged. So, one PN junction of a transistor is reverse biased, whereas the other is forward biased. So, in the figure we can see that this is emitter, this is base, this is collector. So, this is P and N type of transistor. So, here what we have done, we have provided a positive voltage to P side and negative voltage to N side. Similarly, we have not given any biasing to the collector and base junction or collector and base portion. So, forward biased junction of a PNP transistor. We can see here that is the same similar thing that is in that we have done in the PN junction PN diode. So we are providing negative to N side and positive to P side. So what will happen? The positive will repel the holes in the majority of holes in the P side, and the negative terminal repels the majority of electrons in the N side. So they will cross the junction, that is this junction, this particular junction, they will cross, and the negative ions are created on the P side and the positive ions are created on the N side. Similarly, a reverse bias junction of a PNP transistor is provided between base and collector. So the collector has, because it is positive, so it is connected with a because this is P, this is N, this is P. So positive is connected with a negative terminal and negative is connected to the positive terminal. So this is basically reverse bias. So this is reverse biased, and this portion is basically forward biased. So we have forward biased in the emitter base junction and we have reverse biased in the base and collector junction. So we have both the currents, like emitter current in the base current in the forward junction, and similarly we have minor current or in a microampere current at the collector side. So these two diagram depicts about how you can forward bias a PNP transistor or how you can reverse bias a PNP transistor. Only the thing you have to see that emitter base junction should be on forward biased and then base collector junction should be on reversed biased. So one PN junction is to be forward biased and one PN junction is reversed biased here. So next, what we have combined both the junctions. Now emitter and base are in forward biased. So positive is connected to positive terminal and this is negative, and negative is connected to negative terminal. Similarly, collector is positive, so it is connected with a negative terminal, and this base is negative, so it is connected with the negative terminal. So this is your forward biasing and this is your reverse biasing. So the current, because it is a P or PNP type of transistor, so the current will flow from emitter to base side. So the current is input towards the emitter side. So this is current, your IE current. Similarly, the base current, that is from N side to the collector side, that is the base current. Similarly, the collector current is from negative, because it is P side, so the current is flow from P to N side. So always you have to remember the current will flow the path that is P to N side. So both biasing potential have been applied to a PN transistor and it results majority and minority carriers flows indicated. So majority carriers plus will diffuse across the PN junction, forward biased PN junction, into the N type of material. A very small number of carriers will now in the N type material to the base terminal. So resulting is IB is typically in order of microampere. So here IB is in microampere, IE is in milliampere. So we have to see this because we have been given forward biasing to emitter base junction. So obviously this current is maximum, that is IE, and IB is very much less. So the large number of majority carriers will diffuse across the reverse bias junction into the P type of material connected to the collector terminal. So because we are providing here negative terminal, so all the holes are attracted towards the negative, and similarly all the electrons are attracted towards the positive terminal. So the number of electrons will cross here will give you the some current, that is IB current, which is very less, and similarly the IC current, which is very less. So majority carriers can cross the reverse bias junction because the injected majority carriers will appear as minority carriers in the N type of materials. So when we apply KCL here, so you can see when you apply KCL here there are three currents, IE, IB and IC. So IE is the input current, IB and IC is the outward current. So we can write this equation, that is IE is equivalent to IC plus IB. So this comprises of two components, the majority and the minority carrier. So what is majority here? That is IC is composed of two components. First one is the majority, that is IC majority, and the second one is the IC minority carrier. So here ICO minus IC, that is majority minus minority carriers current with emitter terminal open, and it is also called as leakage current. So if we see that IC O minus IC current. So this will give you a leakage current. So next we have different configuration of the BJT, that is we have three types of configuration basically, because we are providing a PNP or NPN transistor. We can have a common base configuration, a common emitter configuration, or a common collector configuration. So what is here? The first is the common base configuration. So the common base terminology is derived from the fact that the base is common to both input and output of the configuration. So here we can ground both the base, and it is common to both the emitter and the collector. So the base is usually the terminal closest to or ground potential. So as I have said you that the base have to be ground. So all current direction will refer to conventional, that is whole flow, because that is from P to N side, and the arrows in all electronic symbols have a direction defined by this convention. So we have to follow the initial convention, that is from P to N side the current will flow. Note that the applied biasing voltage sources are such as to establish current in the direction indicated for each branch. So we have to note down this also. So coming to the picture of common emitter, common base configuration, we have the base, that is P and P. We have the base which is grounded. So this is grounded. We have emitter voltage is provided to the emitter, because this is your emitter, this is base, and this is collector. So the voltage is VEE, which is in forward biasing. This is forward biasing. So this is VEE, and the second one is a reverse biasing, which is VCC. So we have the current flow from the emitter to, because from P to N side the current will flow. So from emitter to base the current will flow. Similarly, we can draw the actual picturization of this, because we have to show that what are the different currents will be flow in the PN junction transistor, PNP or NPN type of transistor. We have taken here the PNP transistor. So the current will flow from PN and P, from P to N side. The base has different current, which is also, the base is grounded. So this is your ground. We are provided here the positive VEE, which is positive terminal is connected to P side and negative terminal is connected to N side. Similarly, the negative terminal is connected, this is your VCC. The negative terminal is connected to P side and the positive terminal is connected to N side. So this is your forward biased and this is your reverse bias. So here we can see that the current will from IB, from IB to ground. This is the current, the base current. The collector current is IC here, and the emitter current, which is IE here. So the current always flow from P to N side, from P to N side here. Only the base current is follows the ground path. Similarly, we have NPN type of transistor. So in the same way, we have emitter, base, and the collector. Because it is the N type of material, so we are connected here, the negative terminal, and the positive terminal is connected to the P type of material. Similarly, positive is connected to the collector, which is N type of material, and negative is connected to the base, which is P type of material. So here, what will be the actual picturization? We can see symbolically, that is emitter, base, and collector. The current will flow from, because it is NPN, so this is N, this is P, this is N, P to N side. So the current will flow from P to N side. The emitter current is also from P to N side. You can have this current, that is IE. Similarly, the collector current, that is from P to N side, that's why the collector current is IC. And the base current, because this is from P to N side and the base is here positive, this point, and this is the negative point. So the current is from P to positive to negative side. So the base current is here. So VE is here provided, that is the voltage at the emitter, and the collector voltage, that is VCC, is also provided. So again, we have this portion is reverse bias, and this is your forward bias. So to describe the behavior of common base amplifiers, it requires two set of characteristics, the input or the driving point characteristic or the output or the collector characteristic. So we have 2 points of characteristic, either it will be an input characteristic or output or the collector characteristic. So the output characteristic has 3 basic regions. The first region is the active region, the second is the cutoff region, and the third region is the saturation region. So from the graphs you can see that there are 3 regions mentioned, that is the cutoff region, active region and the saturation region. So the active region defined by the biasing arrangement. So whatever the forward biasing is there, so that portion is basically the active region. The cutoff region is the region where the collector current is 0 ampere. So the cutoff region is where there is no current flowing in the collector circuit, and the saturation region is the region of the characteristic to the left, that is at VCB is equivalent to 0 volt. So we have drawn here the common base configuration, that is VCB. Here we have taken the common voltage for the base, that is 1 volt, 10 volt and 20 volt, and for these common voltage for the base we have drawn the characteristic curve between VBE and the IE. So the base emitter voltage and between the emitter current. So here we have a scale of 0.2 difference in the x-axis and a scale of 1 difference in the y-axis. So when you plot, it is similar to PN junction diode, that is after a certain point, that is your knee voltage, the current will start sharply increasing. But for common voltages, common base voltages, we have different type of current shown in the picture. So for 1 volt we have lesser current as compared to 10 volt as compared to 20 volt. So when you increase the common base voltage, so for a common base configuration, when you increase the voltage here, so for different voltages we have maximum current. So we have for 1 volt lesser current, for 10 volt it is increased to somehow maximum to 1 volt, and then for 20 volts it is more than 10 volts. Similarly, we can show the configuration, that is this is IB, which is the common base current, and this is VCB and this is your IC. So here the cutoff region is what region? Where the collector current is 0. So this region is particularly jahan par collector current there is 0. So that region is called cutoff region, and the saturation region is where ICB is less than 0. So ICB is this point, and below this, that is the less than 0 is VCB is equivalent to 0 volt, and to the left of the VCB is equivalent to 0 volt, there is a saturation region, and behind apart from the saturation region there is one more region which is called as active region. So active region is where the current will starts rising. So for 0 milliampere the current is very less, for 1 milliampere the current is high, then for 2 milliampere the current increases to then 3 milliampere, then for 4 milliampere. So for different base currents we have different currents for the collector. So we can draw these curve for the common base configuration characteristics. So next we can show the picture. This picture basically shows the difference between active region, saturation and cutoff region. So I is increased here, IC is increased here in the active region. BE junction, that is the base emitter junction, is forward biased and the collector base junction is reverse biased. Refer to the graph is IC is equivalent to IE. IC does not depend upon VCB and it is a suitable region for the transistor working as an amplifier. For the saturation region, we have base emitter and common base collector base junction is forward biased. Both the junction is forward biased. Either it will be a base emitter or a collector base junction. Small changes in VCB will cause big difference in IC. The allocation for this region is to the left of the VCB, that is equivalent to 0 volts. Similarly, for cutoff region, the region below the line of the IE is equivalent to 0 ampere, which I have shown you here. That is below the line, that is IE is equivalent to 0. That is the cutoff region. This is your IE, the cutoff region. So VBE and BE and CB, that is the batch base and emitter, and the collector and base is reverse biased here. So no current flow at the collector, only there is leakage current. So in this graph we have the cutoff region, and in this cutoff region there is no current. This is no current. So we can see that in cutoff region there is no current and there is only leakage current. We have only leakage current. So this is the difference between the active region and the saturation region and the cutoff region. So next, the curve output characteristic clearly indicates that a first approximation to the relationship between IE and IC in the active region, and which is given by IC is equivalent to IE. Once a transistor is in the on state, the base emitter voltage will be assumed to be around, for silicon, that is base emitter is 0.7 volts. So up to 0.7 volt there is no current, but above 0.7 volt there is a sharp increase in the current, which can be shown in the figure below, that is between IE and VBE we have this type of current, that is at 0.7 volt there is a sharp increase in the current. Below 0.7 volt for the forward biasing, because we are providing here forward biasing at VBE, we have no current. So up to this point what we have discussed about the common base configuration, what are the different type of transistors, that is PNP or NPN type of transistors, how this PNP and NPN type of transistor can be formed with the combination of both these diodes. Either you can combine PN or PN type of, that will give you a NPN type of transistor. Similarly we can combine NP or NP type of which will give you NP or PN type of, which will give you a NPN type of transistor. So in the next lecture what we are going to see about the common collector configuration. This is the common base configuration where the active region and the saturation region is shown in the plot, and we have drawn a graph between the emitter and the collector emitter, emitter current and the collector emitter current, and taking the base current as a common current, or the base voltage as a common voltage. So as you increase the base voltage, as you increase the base current, there will be a sharp increase in the emitter current. So in the case of the forward biasing, for the collector configuration we have to see what will be the characteristics. So similarly we will see about the common emitter characteristics, common emitter configuration characteristics, by plotting the graph between the common emitter configuration, what are the different X layers and the Y layers parameters which we have to show in the plot. So for this we have to next see what are the relationship between these collector, emitter and the base current combination. So with this I want to end this lecture, and in the later on lecture we will continue with this configuration of the PNP or NPN of type of transistor. So we will see about common collector, and then we will see about common emitter configuration. Thank you so much.